Yeah, I'm going to present a somewhat different method to try to detect movements at the seafloor. And this is the result of a 5-year, actually 7-year project funded by the European Union with partners that you can see identified below. The name of the project was FOCUS, which meant fiber optic cable use for seafloor studies of earthquake hazard and deformation. So kind of the same topics we just saw earlier. The primary working area is offshore Catania in eastern Sicily. So we're in the Mediterranean, just offshore Mount Etna, the largest, most active volcano in Europe. And I'm hoping you can see my mouse. Yes, you can. So there are strike slip faults allowing the gradual sliding of the edifice of Mount Etna sort of into the sea. And there is a major strike slip fault here, which was mapped in recent years. And there was some seafloor geodesy done by the Germans, but in this case, it's acoustic distance ranging using this network of 5 stations here. And they detected a 4 centimeter slow slip event back in 2017, which was dextral strike slip. And they also had pressure sensors and showed some slightly down to the north, 1 centimeter of down to the north normal faulting motion. This area is kind of special, aside from the fact that there's a big volcano and a strike slip fault, because there is a 29-kilometer long cable operated by the Physics Institute as a prototype for a neutrino observatory. And so down here was a seafloor observatory from which one could connect a cable, a fiber optic cable, which is what we did, and then just deploy the cable across the strike slip fault in a sort of a zigzag pattern. And then these little yellow triangles you see there, that was a seafloor distance ranging, so seafloor geodesy network, which we also deployed. And one of the major questions that we're asking here is, where is the lateral slab tear of the subduction zone? Because for those who might know, there's a small subduction zone beneath southern Italy, creating this volcanic arc, which are the Aeolian Islands. And as the slab rolls back, there's this lateral slab tear here. And it happens to be basically exactly where the strike slip fault is and where Mount Etna is located. So that was the tectonic target of this study. Now, the way it functions, you send light down a fiber optic, down an optical fiber, in very short pulses, nanosecond pulses of light. And there are 3 backscattering phenomenon. One is called the Rayleigh phenomenon, the other one's Brillouin, and the other one's Raman. The Rayleigh phenomenon is the strongest and is sensitive to vibrations. So if you imagine plucking a guitar string, seismic waves, ship noise, marine mammals, whales calling, all of this can be measured by DAS and there's a whole growing literature on that. The next phenomenon is the Brillouin backscattering phenomenon, and it's sensitive to long-term strain and temperature changes. And that's what the Brillouin phenomenon is, and that was what I used during the FOCUS project. And then the final one is Raman, which is sensitive only to temperature. So in this presentation, I'll be talking about mechanical strain and also somewhat a little bit towards the end about temperature change if I get there. So here is the 3D view of the morphobathymetry of the seafloor. This is the bottom of the Malta Escarpment. You can see the strike slip fault here. You can see the path of the electro-optical cable, and the star is the seafloor observatory. So in dashed is the strike slip fault, and this is where we constructed according to design 6-kilometer long fiber optic cable. It had 5 active optical fibers in there, which we connected in a 3-fold loop and a 2-fold loop, and it had 2 different kinds of fibers: tight fibers, which are more sensitive to mechanical disturbances, and loose fibers, which is the industry standard, which are not very sensitive. They're not supposed to be very sensitive to mechanical disturbances, because that's the way the telecom industry wants it to be, because if something kicks their cable, they don't want it to break their fiber, to make it simple. So we worked with an ROV. This is the Victor remotely operated vehicle of Ifremer. It's rated down to 6,000 meters. The first thing we did is we performed a high-resolution microbathymetric survey to try to find the ideal path to deploy the cable. There really wasn't an ideal path because it was really quite rough on the seafloor. Here you can see the ROV Victor with its robotic arm connecting our cable onto the seafloor observatory. That's the moment of connection. And we had 6 kilometers of cable wrapped up on this reel on a plow. And by pushing this plow with the ROV, we tried to deploy the cable 20 centimeters below the seafloor in a little furrow to protect it from, well, disturbances and to improve coupling to the seafloor. Anyway, that was the plan. Reality is often different than the plan. We'll see that also in a bit. So here you can see the general microbathymetry made by the Victor. The black line is the cable track. The white triangles are our acoustic distance ranging seafloor geodesy stations. And this is an acquisition just a couple weeks after deployment. So we deployed around the 20th of October. And by the 8th of November, we see here an acquisition. Everything which is close to zero means that there's been no mechanical deformation. Everything is positive, means you have some strain, and this is along the distance. And this is it repeats the distance 3 times. Once along a loose fiber, goes back along a tight fiber, and goes back again along a tight fiber. And now, in comparison, I'm showing a same kind of measurement from about 9 months later in August, and superposed over the previous measurement. So basically, this is just oscillating, about 5 or 10 microstrain above and below zero. Basically, it means that nothing's happening. This is what we call it's a sampling noise. It's the error of the measurement. But by 9 months later, we see that distinct peaks have formed at the first fault crossing at 2,500 meter distance, a smaller peak at the third fault crossing. We see these peaks in the loose fiber, but we see them much more strongly in the tight fibers, and the values are about 30 to 40 microstrain in the tight fibers. And this would be the equivalent, and it felt over a distance of a few hundred meters. So when you integrate the strain over those few hundred meters, that's the equivalent of about 1.5 centimeters of elongation at this location. So at the time, this looked very encouraging, and we thought that the strike slip fault might be moving and that we had recorded elongation using this method. And again, this is sort of idealized what the method should show, because we're crossing the strike slip fault at an oblique angle each time. And for dextral movement, you should get elongation here, shortening here, elongation there, shortening here. So this would be sort of an idealized signal. If we had as a second possible origin for the deformation a downslope current in this sort of gully ditch that's located here, then we would expect elongation everywhere where it touches the cable. And indeed, the signal we observed wasn't exactly this and it wasn't exactly that. It was sort of in between the two. And I think I have just lost my ability to advance, which is a nuisance. I'm going to have to stop sharing and restart again. Sorry about that. That happens sometimes.
No worries.
So with a little luck, it should be working again. Okay, it is. So this shows the success of our burial on the seafloor. So when the seafloor was flat and soft, we were able to bury the cable in this little furrow in that ditch. That's a tiny fish on the seafloor. And when the seafloor was rugged and rough and hard and indurated, then we had to go up and over it with the plow. And so the cable is spanning across high points. And that's not ideal. This shows an observation along the entire 29 kilometer plus 3 times 6 kilometer path length. This is on the 19th of November. This is on the 20th. This is on the 21st of November. And we can see basically on the 19th of November, everything is more or less oscillating around zero. And then on the 20th of November, we can see these signals start to develop. And so basically, there was a natural event between the 19th and the 21st of October affecting primarily the first fault crossing and a little bit the third fault crossing. This natural event also affected the electro-optical cable 6 kilometers offshore, as you can see with this sort of two-part signal, with elongation here and shortening there. So some event affected the cable about 300 meter depth where there is no fault, and it also affected the cable down in 1,800 meter water depth where it was crossing the fault. And if it's the same event, then it probably was not a tectonic movement. What we did in September of 2021, we wanted to improve the coupling of the cable, which is so spanning, as I was pointed out in many places, by putting sandbags in these locations on top of the cable. I didn't want to touch this area where we'd seen the strong signal, but tried to do it on the sort of the back 3 kilometers of the fiber optic cable. These bag drop operations were done with an industry ROV There's the arm of the industry ROV. There's a 25 kilo sandbag. There's the cable on the seafloor. There's already the previous bag having been dropped. And we dropped about 20 odd bags um, at 5 kilometer spacing in 5 different places. And there were also some bags dropped up here, so in 4 other places. And now you'll see the signal of those bag drops in a moment. So this is one recording per month over a 21-month period. And this is the initial recording, so everything's close to zero. This is 1 month later where we see the natural event with that elongation about 2.5 kilometers from the observatory. And then that signal sort of persists for a long time. These are the 4 bag drops at the 4 bag drop locations, and you can see by putting the bags on, and this is the pellet bag drops at 6 kilometers, and we also pushed the plow, which was kind of dangerous and nearly broke the cable, but luckily the cable was sturdy and it survived. And so you can see we created these 4 bumps of about 50 to 200 microstrains, so very significant signal at those 4 locations of the backdrop because we pushed the cable down into the mud, thereby elongating it in those places. And now we can see how the signal decays over time. So this is the first 21 months, and then if you keep going ahead in time, there were some interruptions due to, well, sometimes incidents in the laboratory, and sometimes we also took the interrogator off to Guadeloupe to perform other measurements, which I may or may not have time to show you towards the end. But the story is that these 4 easily seen bumps up here from the backdrops, they decay as the months go by, and about a year or 2 later, those signals have disappeared, and there's probably another natural signal coming in here. So and here are the seafloor geodetic stations, so these acoustic ranging stations. This is a Canopus model manufactured by Xblue Exail. These are Sonodyne models, and they acoustically ping each other. And so they're set up on both sides of the fault. We have 8 Canopus over here and the 5 Sonodynes over there. And after 1 year of data acquisition, there was no change in the baseline lengths, no statistically significant change. And there was also no change in the period in November 2020 when we observed the elongation signal here. So we think that the strike slip fault did not move, and either the fault is locked or it might be creeping very slowly just at sort of the detection limit of our acoustic baselines. So these are the take-home messages from the Sicily study area. We detected a natural 1.5 to 2.5 centimeter strain event at the first fault crossing. The elongation is most clearly expressed by 40 to 50 microdepth signals in the tight fibers, but it's also visible at about half the amplitude on the loose fiber. And the cause of this signal is probably a bottom current, which affected the cable 300-meter depth at 6 kilometers offshore, as well as down 1,800-meter water depth, about 25 kilometers offshore. The cable is not well buried over at least half of its path length, probably more, and yet we managed to observe deformation despite poor coupling. And this is exactly the same configuration as telecom cables have. And the elongation signals from our backdrop experiment were very visible, but they decay over periods of several months to 1 or 2 years, losing about half the amplitude within a year, and after 2 years they've disappeared. And so now I'm going to try to tell you in 5 minutes what we're doing in Guadeloupe, where we have a network of commercial telecom cables connecting the big islands here in the north to the little islands to the east and south, with cable distances of about 30 to 60 kilometers. This is a network of cables that was deployed in 2019 with more fibers than are needed for telecom, because there's only 30,000 people living on these little islands, and they have 12 pairs of fibers, and 3 are used, and so 9 are unused. And so they allowed us to work on the unused fibers. And so this is in cooperation with the Région Guadeloupe, who owns the cables, and Orange, who operates them, and the University of Guadeloupe. And so we performed measurements at first every 6 months. And then when I realized that we were seeing temperature changes, we started increasing our cadence to measure every 3 months. And what you see in yellow here is the sea surface temperature as measured by satellites in this area. And when we average I should probably go to this one first. All right, this is a bathymetric profile between Saint-François and Marie-Galante. So this is very shallow. This is like 30, 40-meter depth. These are coral reefs. Then we get deeper, it gets down to 700-meter depth max. And then we get shallow again when we go to Marie-Galante. And what we see from each measurement is that sometimes we're higher and sometimes we're lower. And it's fairly systematic, like almost a horizontal line, which is just higher and lower. And now and if we average these 20 kilometers of data, and I'm going to try to go back to the previous one, and I lost it again. Oh, damn. Uh, I've lost it again. I'm sorry. Ah, here we go. Okay, it did work. Here we go. So the sea surface temperatures in yellow, our measurement, considering the original data point from June 2022 to correspond to the surface temperature of 27.9, and thereafter we calculate the delta T, and that's these colored bars here. And we can see that the colored bars correspond to the sea surface temperature within about a tenth of a degree each time. And since June of last year, we started performing continuous measurements from a Orange telecom link here in Saint-François. And so we've got some data since June of last year, which are now continuous. And now I'm going to try to, oops, there we go again. So this is the area where we see the systematic increases and decreases in temperature. What we also saw, and which is really important, and I didn't mention, but I'm sorry, here we go, is that between 2022 and 2024, the water temperature increased by 1.5 degrees, which was actually an enormous increase, and it also corresponded to coral bleaching with 30% losses in Guadeloupe. And so what we observed there was a marine heat wave. And so this is again the measurements from Saint-François to Marie-Galante, where we see these systematic upward and downward shifts over the shallow coral platform. We also see these sharp upward and downward breaks at the shelf break. And this is where last year we deployed some current tilt meters in these red circles, and two more were deployed in June. And in June of this year, I plan on deploying some current tilt meters and temperature sensors at the shelf edge here and down in the canyon at 700-meter water depth. And so this is where we see these systematic temperature shifts. And what's very interesting here near La Désirade, and getting back to movements on the seafloor, this is not just shortening or elongation, this is alternating both types of signals. It's very strong positive and very strong negative signals about every 300 to 500 meters. And so I think that this is the effect of strong currents and then the narrow strait, which are pulling and tugging on the cable as it's emerged in the seafloor. This is an example of an oceanographic model showing very strong currents just south of La Désirade in this narrow ocean passage between the island here and the next island there. And now I've got a couple of nice scenes of divers installing the instruments on the seafloor. So these are the divers, and now they need to fix them on the seafloor, otherwise they're going to like wash away. And so they're hammering with hammers and cords and attaching these instruments. And that is the current tilt meter. It's now fixed on the seafloor, and there you can see the very strong current moving the divers and the tilt meter back and forth. And so we'll be recovering the data from those instruments in June of this year. And with that, I'm wrapping up. Thank you very much.